All right. Thank you very much, Sanjala. I've got some, but looks like Stephen has his hand up first. Stephen Blaber. I'm not sure how to pronounce your last name.
Yeah, thank you for the interesting talk. I was a bit interested in because you're doing like a realistic architecture, have you done any comparisons to like what people would typically do for these types of bit erasures in these CMOS bits, and how does it compare to like what you've done here? Like where would a real
Yeah,
like where would current methods lie on this curve or something like that?
right. That is sort of the next step. So stay tuned. Um, do you have specific things in mind when you say current methods?
No, I'm just wondering like a comparison between what you've done and like what like a just a typical bit that isn't optimized would how it would perform.
You mean in current computers?
Yeah, current computers, like just a regular CMOS bit that's not optimized.
Okay, so CMOS right now operates at higher voltages than we're using here. So we're kind of assuming a nanoscale, small scale system. So CMOS operates at higher voltages and it's gonna incur, so let's see. I don't have exact numbers off the top of
Hmm.
my head, but they should be several orders of magnitude beyond this picture.
Mm.
But I can tell you that the time that's involved in a bit erasure in current computers, knowing that they operate at 3-ish gigahertz, is going to be so that's several hundred picoseconds, which is also maybe an order of magnitude or a few orders of magnitude higher than this time, which is on the order of like tens of picoseconds in terms of speed. In terms of dissipation, yeah, I'm not actually sure, but I think that it's it's not quite a fair comparison because
Hmm.
we are dealing with also much higher. So current computers have a much lower error tolerance, maybe 10 to the minus 5 of error, whereas here we're saying maybe 10 to the minus 2 is sufficient for a bit. So yeah, thank you for
Okay,
the
thanks. Yeah, that's useful information. Kind of puts it in the bigger picture. Thanks.
David, you're up next.
Yeah, nice talk. I guess I'm curious, do your findings make any suggestions of like tweaks to the architecture that would give better trade-offs if you were going to start from scratch and build a new circuit?
right. Well, we built this model to see how far we could push the limits of CMOS as is. And so if we were to build a new architecture, we would have to build a new model that incorporates that architecture and can describe the thermodynamics there. However, what I can tell you is that although I haven't shown it, we have some beginnings of ideas of why the optimal protocols are the way they are. Basically, it tells us that we want to maximize the current through this access transistor and not through other parts of the circuit because we want to basically most efficiently drive the current through the part of the circuit that's actually doing the erasure.
Hmm. Hmm. Cool. Thanks.
All right, I've got a few questions for you, Sanjala. Very, very nice talk. Very speculative questions. First, interesting your emphasis on the housekeeping heat in the human brain. A lot of the cost, a huge, I'm not sure the precise amount, but my understanding is a vast majority of the cost within neurons is just maintaining things like the gated ions ready to fire. At a larger scale, even there's what's called things like the default mode, where it would appear that you're not actually doing anything at all. Your brain is just sort of sitting there, maybe daydreaming, the engine's idling. And again, that's a massive amount of the cost. And that can be viewed sort of, I guess, as analogous to housekeeping heat. So I was wondering if you had any ideas about some analogies between what you've got here and neurobiological kinds of thermodynamic processes. And then the other question, which is a little bit more concrete, following up on the one that we just heard, was do you have any ideas of real computers don't actually do bit erasures? They do much more complicated things. very, very complicated sets of gates that are all intertwined with one another. Do you have any idea of how your results in this abstracted model of CMOS might extend when we've got a whole bunch of such things connected together, all modeled in this kind of a way? So two very
Yeah.
separate questions.
Yeah, those are great considerations. For the housekeeping heat, well, I told you that depending on the level of the bias that we have, there we get different amounts of housekeeping heat. So I guess the analogy would be how active maybe is your brain, or how, okay, that I'm sort of making things up here, but maybe there's an analogy to how which parts of your, well, how active is your brain, and can we, okay, never mind. I think the analogy is just that it does require power to keep your brain on, just like it requires power to keep your CMOS circuit on. And so that power is something that we have to account for. So the takeaway for my system is that basically we want to minimize the amount of time we spend on this operation, because we have to keep in mind the power costs. And so where are we in the regime where the power of keeping the machine on is higher than the power associated with actually doing the operation? So we want to balance those two things. And then to address your more concrete question of can we scale up, that is in fact the next goal, is now that we have a model of bit erasure, we can potentially connect many of these bits together in whatever architecture you'd like. We can also connect not just NOT gates, but also other gates that we can model in similar ways and compute the dissipative costs through those more complex circuits as well. So yeah,
Okay.
that is the next step.
Okay, great. Thank you very, very much.
Thank you.
And Francesco, are you there? You're good to go, Francesco?
Hello, can you hear me?
Yeah, we can hear you. Nothing is showing on the screen, just your, yeah. Okay, it's not full screen yet. There we go. You're good to
Can you
go.
see the mouse as well, or
Yeah. Mm-hmm.
just? All right. So first of all, thank you very much for the opportunity. This is work in collaboration with David and Abhishek Yadav. Most of the credit, I should say, like it's this work I did when I worked in Los Alamos, but now I moved from away from Los Alamos. But I guess I'm still guest scientist there. So this is the outline of the talk. It's hopefully like a little bit less than half an hour, so that who keeps track of time is happy. But David, I guess, and there is a paper which is already on the archive that you can go and have a look, which is this one. It's gonna be updated very soon with a little bit more results. But the idea is I'll give a very brief introduction to very brief on stochastic thermo. I don't need to tell you much about it, and essentially talk a bit more about mismatch costs. And then we'll go into a little bit of the details, and I will discuss how to compute the mismatch cost for computer codes and simple models of computers, particularly using GRASP. And then we'll move on and we'll discuss sorting algorithms, okay, at a higher level, and we'll have a very brief conclusions. Stochastic thermodynamics, here's the one-liner. I guess, it allows you to describe out of equilibrium, give names to what is work and what is heat, or heat change and work changes. There is a very nice paper by Vanderbroek and Esposito. I will advise to have a look, but there are plenty of very nice reviews out there. And the two-liner version is, it allows you to extend the first and the second law are completely out of equilibrium. So for instance, like, from evolution of probability distributions, you can essentially make sense of work rates and heat rates and give definitions to internal and external entropy changes. And by doing that, you essentially reconstruct Prigoghine's second law. That was derived in irreversible thermodynamics, but very close to equilibrium. And in this case, it is true completely out of equilibrium. This is a shameless plug. There are 2 papers that appear on the archive. There are some operator-based uncertain relationships and some no-go theorems about quantum batteries. If you're interested in this work, go and have a look. It's a very nice work by Pratik, my previous postdoc. But this is a talk about computation. And in, well, you probably know this, sentence information is physical. It has to do with Szilard and Landauer, essentially started to think about processes at a nanoscale. And fast forward several years, then you can start to think in terms of what is the interplay between how information moves on a computer and how entropy production occurs. According to physicists, I would say, computation is, if you want, is a dynamical system. You can think of it as transitions between states. Computer science theorists would they would like to think in terms of deeper questions like decidability or resource costs. And for computer scientists in general, resource cost means time and space. But that this computer is running and it heats up, so energy and entropy production is maybe something we would like to keep track of. The discussion I'm going to have now is based on there is a very nice review paper on by David and the original paper by Artemi and David, and both of them are in this call. So a computer is a complicated object. We saw a little bit earlier. If you go and look at how a chip nowadays construct, but not even a chip nowadays, a chip around, in 1976, let's say, or 1971. There is a huge amount of complexity. You have, even in an Intel 8086, if you go and look at the number of circuits that you can activate, and you go and look deeper into them, essentially you see there are logic circuitry that you activate when you flip a register in. And there is a lot of auxiliary, let's say machinery you need to keep track of. For instance, like you have the CPU that does some of the computations that we'll discuss in a little bit. You have logic units, and you have a program counter. And at a higher level, and this is essentially at the level of registers and logical circuitry. At the higher level, you have programming languages, and programming languages, they can go from almost machine level, which is you get a glimpse of it here on the right-hand side, but also can go higher level to higher level programming languages, MATLAB, C, and so on and so forth. If you do believe that information is physical, you should be able, just by looking at the flow of information, even at the level of high-level programs, to estimate how much entropy production is occurring at the level of a circuit. And this is what this talk is about. It's probably the stupidest talk you saw today. You see an application of mismatch cost in certain cases, but in general, like there is some work to be done in order to get to calculate the mismatch cost for these programs, and that's what I would like to discuss. This is a picture of a chip. This is actually a modern one. Also, communication is something you can look at. There is a very nice paper by Abhishek Yadav and David I think it's on the archive already. And you saw the talk by Maran on logic circuitry. This talk is essentially like something that matches, that bridges between the, simplified version of the CPU and higher level programming languages. Here is the dichotomy you need to think about. In the previous talk that you saw, essentially, you have a very nice model of essentially of a register. If you go and look at how, for instance, a NOT gate is actually constructed in a circuit, you'll see that you have several CMOS elements, like you have a PMOS and NMOS. But at the highest level, you have just a NOT gate, and this is represented just physically as a particular transformation. At the highest level of description, you can think of a NOT gate as just a map that flips the state of a bit. But you can also go a little bit deeper and think of the input and output as having 2 registers. And then you need to think of these flips as transitions between 4 possible states. So depending on what at the level of description you decide to stay on, like you have different level of entropy production. And this is because of coarse graining. So in principle, you need to choose a particular layer and then try to do calculations at that particular level of description, and then you try to derive some certain theorems that describe how essentially different layers of descriptions, like different layer of coarse graining, for instance, how the two entry productions are related. And in some of these papers describe, I'm not going to describe this in this paper, in this talk, but in the paper with David and Abhishek, we describe that a little bit. Second level that you need to think about is the input. You can think of the input as being deterministic or as probabilistic. And in stochastic thermodynamics, there was a very nice talk earlier. Stochastic thermodynamics is in terms of probability distributions. But when you run programs, you don't think as inputs as probabilistic, but in practice they are. If, for instance, you write a poem and you write 100 times a poem, you'll get likely 100 times a different poem. And that's might be for different reasons. Maybe 100 people are writing the same, trying to write the same poems, and the 100 people are different, okay? Or you are yourself different every single moment in time you write this this poem. And so, like, at the end of the day, once you input the poem inside your computer, you're gonna, you can think of all possible inputs as being described by a probabilistic distribution. And this is the same as the description that also Shannon used in for channels, essentially. On top of this, we also need to add the fact that your device that you're inputting lives into an environment, so it's dissipating some heat. And stochastic thermodynamics is perfect to describe this type of processes. In particular, here is the mathematical framework. We will assume that essentially there exists a process that, if you want, evolves from probability distributions, and this process will be called G. And all that G does is to describe how probability distribution at time t essentially evolves a prime time t plus 1. So this pt plus 1 is GPT. On top of this, you also need to consider entropy production. Entropy production, you can think of it as essentially the difference in entropy change, minus the heat that is flowing out of your system. And stochastic thermodynamics heat, which is F here, is just a linear function. And you can think of it as essentially, like, depending on what state you are in, essentially this W, the function W, will describe how much heat in the particular state will be given to the environment. So at the end of the day, I can think of it as having a system that has a probabilistic source. I have certain operations. This could be logical or not. And then I have an environment my system is living in, and I have an assumption about how the heat is dissipated into the environment. Then my system has a description which is given by G, and I have probability distributions that are evolving in time. Now, what's important is that your system can have also internal degrees of freedom, and your probability distribution, your internal states, they need to keep track of that. And in computers, this is important because sometimes you have descriptions of an algorithm that, depending on which computer you run, might have different registers or variables that you're using. And we'll see some examples in a bit. Very good. So, and here we will describe a little bit essentially the notion of mismatch cost, thermodynamic mismatch cost, as introduced by Artemi and David in 2020. Maran described a little bit here. I'll go a bit more into the details, but you can define a cost function by just reshuffling entropy production, entropy change, and dissipated work. And then I can ask, what is the initial distribution that minimizes this cost function? I call that distribution Q0. And now what is very nice is that actually if you subtract the cost by given an arbitrary distribution P0 as initial states, and you subtract the cost at the particular minimum, you can rewrite that minimum distribution, you can rewrite that as a difference of two KL divergences, which is very elegant. And then you can use techniques, for instance, data processing inequality to prove that certain properties that, for instance, if G is logically non-reversible, essentially you must have this quantity here must be positive, and so on and so forth. There are very nice papers out there. I put a few here. The original paper is by David and Artemi. But the question is how to find Q0. So like here, the assumption I will use going forward is, well, I'll have essentially a function G. And I will assume that, because I don't know much, I mean, I will try to be general. I will assume that essentially the heat function is essentially constant over the states, which means essentially that I'm dealing only with entropy changes in all the results I will present later. And given this assumption, essentially, we'll use a simulated annealing to find this Q0, okay, by using this cost function as an effective energy and then reducing temperature as a function of time and doing random changes on the states to see, on the distribution to see, try to find the Q0. It's not, these are heuristics, but it works fairly well in practice, at least for small systems. But what about computing? Something that your computer is a little bit more complicated even than what I just described. So every single, depends on, gigahertz essentially, you have a clock. And this clock in all computers was crystal. I'm actually not sure what's quartz crystal. I'm not sure what they use right now, but I assume some other, maybe more efficient clock. But essentially, all this clock does is resetting, essentially setting zero, going from state 0 to 5 volts at a particular frequency. This means that the computer turns off and on and runs every single process, every identical process every single time. In this paper by Thomas Aldrich, who's I think he's also in the call, and David, for biological processes that they have processes that are periodic, they introduce this idea of periodic mismatch cost, which means essentially if you look at entropy production, in particular mismatch cost for these periodic processes, your Q0 essentially has to be resetted to the initial Q0 for every single run. And this is what we will call PMC later. And for computers, we will use this form of mismatch cost to calculate lower bounds to entropy production. Second factor is that your computer also has memory. For instance, in all memories, you have magnetic cores and things like this. They essentially store processes. For instance, you might have an instruction register that essentially says that if one particular set of registers is 0, 1, 1, 1, essentially you will run a certain logic circuitry. And this must be stored in a permanent memory. Then you also have general purpose registers where you store the program you're running, and then on top of this you also have ALU and CPU that execute your instructions. And this is a simple, we're getting closer to the model we're going to use in a little bit, where you have general purpose registers where you store your information. You have a program counter that tells you like the instructions you're running at that particular time. And at every single run of your clock, essentially you're adding 1 to the program counter. And this is how you keep track essentially of where you are in the program you're executing. Can I know how I'm doing on time? Because we started a little bit later, so I'm trying to keep track.
Yeah, hi. You could go up to 5 past the hour for us to get exactly back on schedule.
Okay.
There'll be 8
All right.
more minutes top of the
Okay,
hour.
thank you. Yeah. So this is thank you, David. This is a model which is very closer to the model that we'll describe in a second, which is called a RASP. So in which you have a general purpose register, you have a set of instructions. This is a universal Turing machine, and then you still have a program counter that you keep track on. So the mantra here is power, compute, die, repeat. If you want, if you know the song, you're probably laughing right now. If you don't know, it doesn't mean anything to you. I'm laughing because I know the song. But essentially, this is the idea that after every single time period, your computer will turn off and turn on. I'll have a Q0, which is the identical for every single time, and then I have a certain map that I'm running. And this map is reading through the instruction set, seeing which instruction I need to run, and then run it, and then update and continue. Now, the slight problem is that, of course, chips are complicated. And actually, I have this book on my desk right now because I'm reading it for other reasons later. But essentially, like, you need to work with simplified models, and this is what RASP is. So RASP is essentially something that simplifies. This is a page of the book where, for instance, like this is for Intel 8086. This book is from the 80s, and then you see there are a lot of instruction sets that are available. RASP simplifies all of this with the smallest set of instruction known that actually allows you to run a general Turing machine. Now, in principle, you can, because now I work for a quantum company, I guess I need to talk about some quantumness. But in principle, you can think of this also for quantum computers. In quantum computers, you have a program, an assembly code that you run that will run certain quantum instructions. There are certain functions, and these are compiled into, certain pulse sequences that activate certain circuits or certain qubits. So in principle, this is generalizable by the year that we have quantum computers, which is not tomorrow. For classical computers, the RASP model is essentially you have a finite control unit that does pretty much what I described so far. Every single time, it will read and write through the same register. You will have an input tape where you describe the instructions you have, and then you have an output tape. And this is actually the model we will use in a second. And these type of models for computation are usually called in the theoretical computer science as random access storage programs, so which stands for RASP. And these are universal Turing machine. So depending on what instructions you run. One example is, for instance, this one. If I write this essentially a theta function in MATLAB on a RASP code, it will look like a set of instructions to this form. Okay, so you see that I'll have to load the value of x into a register. I will compare R1 to 0, and then if this is positive, then you do jump to a certain line. If it is identically 0, you jump to another line, and so on and so forth. So this is assembly-like code. And the lines code are actually stored into this memory register. So it looks roughly like this. You have a control unit, an instruction register, and a program counter. And the program counter is something that is important because you need to know which instruction you're reading next. So these are two examples, like the source code in C and RASP for two particular functions. Okay, very good. So because I'm a physicist, I think in terms of computer science, of maps. And in order to represent faithfully this map, this is what you need to keep track of. You need to keep track of the line, the program counter, which sometimes I call line code, and the registers you're actually storing your information is. And the cardinality of the phase space is essentially the product of all possible states. So you see that this is actually increases exponentially very fast. So like you need to keep track of this type of. So you see some examples soon. In reality, registers are initially initialized to certain values, and not all points can be reached. And typically, when you simulate these systems, you see that not all possible states are reached through the computation, given all possible inputs. But you still need to, store. You don't know which of those are reached in at the initial points, so you'll have to keep track of them. And what we do in this, essentially, like what I will do during this talk, essentially, I will show you how to construct a map, given this map G, given essentially that you have a programming language. I will choose two. For instance, for this particular RASP code, essentially, this is the flow map of given all possible initial values of x, which are 3. I think I've chosen 3 for this case. These are all the possible flow maps that you will see. And this now is what I call G. So this is my G that I will run into the mismatch cost. Now, okay, any questions at this stage? I don't hear anything, so okay, continue. And for this one, I can actually calculate the optimal Q0 using the simulated annealing, and then I can show how the periodic mismatch cost will actually evolve as a function of time. And here the assumption is that my initial distribution is essentially I will pick a random distribution, and I will just do a convex combination with the optimal one. So you see that if t is equal to 0, essentially I am at the optimal one, so I should not have any positive mismatch cost, and in fact, you see this is true. And as a function of this, interpolation parameter t, you see that you have more entropy production for this process. And this is just for this particular Rasp code. So you see that you can turn essentially a code into a qualitative curse of lower bound to entropy production. Now, how do you do it if you have a higher level language? Well, what you need to do is to turn your code into essentially, to make them construct the map, you need to introduce program counters. And so, for instance, like if I take this MATLAB code, I have essentially to go through every line and introduce or measure the calculate, keep track of this extra variable, which is the program code through my code. Now, if the function is simple, then it's going to be simple. But if it is more complicated, I need to do something a little bit more complicated. One example is the sorting algorithm. For instance, like something we looked into, we're actually in a paper that's about to appear. We looked at this sorting algorithm. And for this, for instance, bubble sort written in MATLAB. And it's actually a fairly simple code. So like, I think I have an animation of this. So if you look at how bubble sort works, you will actually scan the vector. And essentially, if you'll actually swap two vectors, two elements, if these two elements are greater or equal, and so on and so forth. And you keep going through the vector n squared time. So like once you get to the end, you will restart from the next one and then could keep going. This is an algorithm that scales like n squared in the worst case. But how can we convert essentially bubble, sorting algorithms at this level into essentially in a way that they can do mismatch cost calculations? Mismatch cost. First, because I have exponentially increased the number of states, I need to keep the length. This is a necessary. It's not a necessity that I need to do in order to calculate the mismatch cost. I need to fix the length of the vector. And in particular, this one example, one restriction that you can do is, for instance, like inputs are only permutations of 1 to n. Okay, so actually I did a little bit more, and you'll see the difference between them. But how do you take this code and actually turn into these? Sorry. I don't think it is showing. Sorry, like I think anyway. So the idea is you need. I don't see. Did I mess it up? Oh, here it is. Okay, so very good. So how do you construct these chains? So here's the phase space analysis. The number of values I have the program counter. I have internal registers or variables that are I and j that actually is the algorithm is going through the vector. I have a swap register, and on top of this, I also have the vector state. Okay, and if you go and look at the phase space, this actually scales badly. Okay, and you can see immediately how complicated it is to actually keep track of the code lines and all the transition state. At every single line, you need to add essentially a function that reconstructs this map G. For instance, for n is equal to 2, it's actually simple. You have only 1, 2, and 2, 1. And essentially, you see that the code, even though this is easy, there are a lot of steps it has to do in order to calculate it. And the only process in which we have and the only mismatch cost only occurs as states are non-reversible. For instance, in this case, they will appear only here and here in your code. For n is equal to 3, which is the length of the vector, now I have to have more states that actually will produce and will have a non-zero entropy production. For instance, we have this one and this one, this one and this